All right, let's also give a round of applause to Paul. Thank you, Paul. Panel. We're super excited for this next talk. It's by Brandon Atkinson. He's going to be talking about building Game Boy Advanced games in Go. So really fun talk. Also pay attention because we are going to be raffling his game in our raffle this afternoon. So give it over to Brandon.
Wait.
I have the mic. Not yet.
So I'm going to slack you a link here, Brendan. Join it.
I say that again, right?
Slacking you a link. I'll fix the thing over. Join that link.
I want to put it some build that's collapsed.
Should I mute myself or leave it on dialing?
Mute yourself.
They're using,
Use the room mic.
it's abstract.
And then to just prevent is share your screen. No, I have to fix it.
Alrighty. Am I up? Am I good?
Yeah, you are.
Sweet. All right. So let's stop talking about practical things and have some fun. I am Brandon Atkinson. Wait, this is.
Sorry.
You can kind of see my slides in there. Okay, yeah, I'm Brandon Atkinson. I'm a platform developer here at Weave, where we primarily use the Go programming language and build internal tooling and a platform for our developers. We're going to do something way less practical with Go today and hack it a little bit to build a working game for the Game Boy Advance. Let's talk about the Game Boy Advance really quick. Many of you will probably remember this console from growing up. It was a fairly popular console. Nintendo sold, I think, like 80 million units, and was the successor to the Game Boy Color, which were successful consoles in their own right. And it was a very nostalgic console for me. Lots of fun games on it, and I'm sure a lot of you remember it fondly as well. If we peek inside, you can see that it's a fairly simple console, mainly just one circuit board and then a bunch of components soldered onto it. You have some external memory, CPU, speaker, link port, pads for all the buttons. And the important thing I want you to notice is the CPU is a 32-bit CPU. It will actually accept a 32-bit instruction set, which is kind of cool. A lot of people think about the GBA as like a handheld 16-bit console, but it can run 32-bit code, which is an important part of what we're going to be doing today. So GBA is our target. So how are we going to get there? Let's look at some of the documentation and tools you're going to need to make this work. TinyGo is a really cool project. It is an alternative compiler for the Go programming language. And the way that it works is it takes all of the goodness of the regular Go compiler to construct its front end. So I don't know if you know this, but the Go compiler is self-hosted, which means it's written in itself. And you can find all of the packages they use for like parsing and lexing and the abstract syntax tree on the Go package website. Which means that you can build a compiler front end that basically reuses all the Go stuff. And then the TinyGo team does this really smart thing where they link all of the Go front end compiler stuff to LLVM, which is another really cool project. LLVM, for the purposes of this talk, we can just talk about it as a really versatile compiler backend. So you can translate your intermediate representation that comes out of the Go front end into something that LLVM understands, and then you get all sorts of optimizations, all sorts of compile targets, a bunch of really great stuff, including the ability to compile for embedded systems like the Arduino or the GBA in this. So that's really cool, right? That's great that we have the ability to compile for the GBA, but how do we write code that will actually do something, right? How do you write to the screen or get input? So the first thing you're going to do if you want to do this is probably what I did. You're going to go out on the internet and say, how do I write a GBA game in Go? And you're just not going to find a lot of stuff. There's not really a whole lot of documentation available because like this console came out in 2000, like, or I think 2001. It's not something that people are really commonly doing. And the instructions there are going to be pretty sparse. Instead, what you're going to need to do is take a little bit of a trip into the past and go look at the early 2000s internet. It's a fascinating place. And there are some really great resources on how to program games for the GBA. The homebrew community was pretty big at that point in time. And so you can kind of get a peek into what was happening then and how to translate it forward. You'll need some basic comfortability with C. You'll need to understand kind of how it works as a language. Go is pretty close to C in a lot of ways, and so it shouldn't be too difficult. And I imagine that looking some stuff up online or maybe even using ChatGPT would help you. I didn't have that available to me when I was doing this, but you could use that. The two resources that I would highly recommend are Tonk and GBA Tech. Tonk is more practical. It's going to walk you through how the GBA works with real examples. It'll give you code snippets. He has a very like personal writing style where you can actually understand what you should be doing as the developer to get things to operate on the GBA. And then GBA Tech is a much more dry, like technical manual. There is no operating system. There are no system calls, right? If you want to do stuff on the GBA, you're going to have to talk to hardware map memory. You're going to have to talk to specific memory addresses. And so GBA Tech is a fantastic resource to understand that process and how you're going to interact with the hardware to do things. And then the last resource that we're going to talk about, this is shameless self-promotion. I built a game called Flappy Boot, the Flappy Bird clone, and it is fully written in Go, almost completely written in Go. We'll talk about that in a little bit. But you can go ahead. It's open source. Check it out. Go read through the source code. As far as I'm aware, it's the most complete example of a game for the Game Boy Advance written in Go. Yeah. So we'll talk about this later, right?
That was me. I forgot I was sharing this.
You're good. So yeah, you can look at this for a reference. If you're like, I don't know how to do this, you can go check out that actual code. And then also you can play it on itch if you're interested in downloading it and getting a copy. So how do we actually, like, let's get into the code. Let's see what this actually is going to look like to talk to hardware map memory. So if we think about hardware map memory, the way that it works is there are specific memory addresses that you have that have special meaning to the hardware that you can talk to configure the display or change how graphics get drawn. How would you do that, right? Like, this is not something that we've had to do since allocators came along, like way, way back. I don't even know when the first allocators were written, right? As soon as we got out of assembly, we stopped having to think about exactly where our memory lives. So this is probably something you've never had to do in your professional career. I certainly have not. How do you get like a uint16 to exist at a specific memory address? And fortunately, even though Go does not allow you to do pointer arithmetic, it allows you to use the unsafe package to kind of get around that and do what we need to do. So this code snippet is something that you'll see all throughout the Flappy Boot code base. And this is how we interact with the hardware so that we can do things on the GBA. So the first thing you'll notice is this memory map.io address. That is the base memory address of all the IO registers on the GBA. They're packed together in 1 kilobyte. And then you'll notice there's an offset. So I say, hey, this is offset 4. The registers are all 16-bit. And so you say offset of 4, this is the 3rd register in the list of GBA registers. Then you convert from this uint pointer to an unsafe pointer. And that conversion allows us to cast to a concrete type. So we can say, hey, this uint pointer is an unsafe pointer, is actually a pointer to a uint16. So you go through all that song and dance, and now stat is a uint16 pointer that points to a very specific location in memory so that we can talk to and interact with the hardware. But that's going to cause an issue because Go doesn't want to share its memory. The Go memory model is very explicit about the fact that, like, if the operating system gives me memory, I don't expect anybody else to be able to touch this. So the compiler will rewrite your code and optimize away things that it thinks is not useful. And you can end up in situations like this, where Go says, hey, I'm going to read the status of the display from main memory and stick it in a register because I need to do some processing on it. And it's going to catch that value in a register and start doing some processing. And then the hardware is going to come along and say, oh, hey, the display status has changed. And I'm going to update my hardware register to let you know something changed about the display. Maybe I'm drawing the next scan line or whatever. And Go is not going to get that update because it's cached the value in a register. And it's going to have all of these invalid bits. And you're going to see crazy weird bugs if this starts to show up, because you're going to be like, I can see the memory. Why is Go telling me it's something different? The way we get around this is a term that was available in C, a keyword available in C that does not exist in Go, and that's the volatile keyword. Some of you might have worked with volatile memory in the past, but the way the volatile works is it kind of makes the programming language go a little bit hands-off with the memory. It says you can't do funky stuff with this, you can't cache this value, because it might change from underneath you. And so every time I ask you to get that value, you need to reach out to main memory, even though it's slow. Go, like I said, doesn't support this idea, but you can do it with a few lines of C. So you'll see these are 11 lines of C where you can get and set memory using the volatile keyword so that you don't end up in this state where stuff is cached. And you can actually do this directly in TinyGo. TinyGo has a volatile package and it has a registers package that you could maybe use if you wanted to like be really purist about using Go. I had some issues cross-compiling that, and I didn't want to debug them, so I just defaulted to C Go, and that seems to be very portable. So that's what I've been using. That's the only C code in the entire engine right there. And you can see both on the left, the header file, and then on the right, the interrupt, so that you can get those calls from Go. The garbage collector is the next thing that we need to talk about. Go has a really fast garbage collector. It's very performant, but unfortunately, the GBA CPU is like 16 megahertz. And even though your entire heap is only 256K, to do a full mark and sweep on 256K on a 16 megahertz CPU, when you need to push a frame every 16.7 milliseconds, you just can't do it. If you let the garbage collector just run like it normally wants to, you are going to drop frames, which for a game like Flappy Boo, that is very uncomfortable because like it's a timing game, it's like a precision game, it's going to suck for your player. And so you have to be a little bit careful about how you let garbage collection happen. Well, there are a couple of different options. So one thing to keep in mind is the way that the default TinyGo garbage collector works, it's actually not the same as the regular Go garbage collector. It's a little bit slower. It's a much simpler mark and sweep implementation. So it is going to run slower. And the default behavior is I'm going to make an allocation until I can't anymore, and then I'm going to do a garbage collection cycle. So if you ask me to allocate memory and I find no space for memory, then I'm going to do a full mark and sweep. And mark and sweep is O of n, where n is the number of objects on your heap, so that can be very slow. So if you run garbage collection more frequently, you can actually pay less of a performance impact. I decided to go a different way and just avoid the garbage collector entirely, because for a small game like mine, it's actually not that hard to just allocate a bunch of stuff to the heap and then just reuse it. So there's this command called print Alex. You can see it in the garbage collector section, where you can actually have the compiler print out like, hey, this is everywhere I had something escape to the heap. And basically just make sure if anything makes it out to the heap, make sure I reuse that resource so that I'm not continually allocating new stuff on it. So like within the first two scenes of my game, all of the memory that I'll ever use has been fully allocated, so the garbage collector never kicks in. That's a great way to avoid those resource solves. So we have some technical details. Let's talk about the GBA itself and how it draws graphics onto the screen. There are several different graphics modes. If you've heard of mode 7 on the SNES, it's a very similar concept. There are modes 0 through 5. A lot of stuff that you'll read online for like Go specific GBA programming will talk about mode 3. Mode 3 is very easy. You basically plot on the screen as if it's a bitmap. And one of the issues you'll find is, again, a 16 megahertz CPU just can't push that many pixels onto a bitmap type display 60 times a second. You're going to get screen tearing and you're going to have issues drawing graphics to the screen fast enough. So we're going to use mode 0. That's probably the one I would recommend for most basic games. It's going to give you 4 backgrounds. It's going to give you regular tiled sprites. It'll give you 32K of VRAM for your sprites. It will give you 256 background colors and 256 foreground colors. We'll talk more about all of this later, but just keep in mind that there are several different ways you can utilize the GBA's hardware. So next, we're going to talk about VRAM. There's 96K of VRAM on the GBA, and it is conceptually split up by the hardware like this, only in mode 0. The semantics will change a little bit if you move to a different mode, but you have 4 different character blocks for your background maps and tiles. So a character block is where you store the graphics data. And then each character block can be further subdivided into, I think, 8 screen blocks. A screen block is 2K. And screen blocks are where you stick the tile map, right? So a tile map indexes a tile. The tiles are stored in the character block, and you can use those together to construct a background image. You additionally have 2 character blocks of sprite data. So this is for all of the animated objects in your game. And that is a separate section in memory. You can stick your sprite data there and then reference it in the next segment of memory we're going to talk about, which is OAM. So OAM is object attribute memory. The GBA has support for 128 sprites on screen at a time, and you write the attributes for those sprites into OAM. So things like the X and Y position, the tile index, the priority for the layering effects. OAM is where all of that's controlled. You'll also notice there's this affine sprite data. It's interlaced with the normal sprite data. We'll see how that looks in code later. But if you've ever seen sprites like zoom in or skew on a GBA, like that's how it's pulled off. It's with an affine transformation matrix. Colors are stored backwards and in 15 bits on the GBA, so you get your blue, green, and red channels, 5 bits apiece. The top bit is unused. Sprites, you get 256 colors. It can be a single 256 color palette or 16 color palettes. Same thing for backgrounds, which gives the GBA its limit of 256 colors on screen in mode 0. Sorry, 512. 512 individual colors because you get both backgrounds, both palettes. Okay, so this is how it looks in code. We have, again, same thing where we're taking a UIC pointer, converting it to an unsafe pointer, then casting it to a specific type. The only difference here is we're accessing slices of memory instead of a single value in memory. And so you can use the unsafe slice package to get access to those values. And you can see I haven't heavily leveraged the type system to try and enforce some safety around doing this, because otherwise it's just a giant blob of UN16 arrays, which can be a little confusing. So the next thing is OAM. You can see it was defined earlier, but we redefined it here for some convenience. You can see the different attributes. Each sprite is defined by 3 different attributes. These are UN16 values. And if we look at the attribute struct, there are 3 values in here, but it's gigantic. So this is common throughout my entire code base, Flappy Boot. There's tons and tons of documentation on how all of the features works. I use this kind of as a way to dump all of the things I was learning and understanding. So the doc comment should be very thorough. You should be able to get a good understanding of how to do things. You can see that we pack the things like the X and Y location, the sprite size, priority, tile map, all get packed into these attributes. And then at the very bottom, you can see this unused OAM value, and that's basically for spacing, because again, the affine transformation matrix is interlaced in with the normal data. And so there's actually 2 slices that sit on top of each other in memory, and they use alternating addresses in order to get at that data. It's kind of a weird implementation feature that the hardware uses, but this is how it's supported in my. So let's talk about the PPU, which is the graphics accelerator for the GBA, and how it draws graphics on screen. So to draw backgrounds, the PPU will first go to VRAM into a screen block where it gets tile map data. When it finds a tile index, it will then go into a character block in VRAM where it finds the graphics data. And then when it finds a specific pixel to draw, it will look up the index in the palette data to say, hey, what color do I need to specifically blit to the screen for this background? You get 4 backgrounds. The PPU will do that for all 4 of them. You can layer them together, and you get this final scene with all of it composited together. So these are your backgrounds. The PPU is also used to draw sprites. So you can see, instead of going to first, it goes to object attribute memory, and it will check the X and Y location of the sprite, the scale, horizontal and vertical flip, and the tile ID. From the tile ID, it jumps into VRAM and says, hey, in the sprite character block, where are the graphics? And then when it finds a specific pixel, then it will jump to the palette and say, what color do I need to flip to the screen? So that's the 2 major pieces that the PPU handles, is backgrounds and sprites. And when you compose all of it together, you get your background and your sprite layers all working together. The last thing is input. There's a single register on the GBA that handles, there's actually a couple, but the basic one is a single register that handles input. This might look like a typo, but actually all of the bits are 1 by default. So if a button is unpressed, the bit is set to 1. And as soon as you press the button, it flips to 0. And so you can read the input state of the control pad by simply looking at the bits in that register. And you can see here's the code where we do that. We get the input register, and then we have a bunch of bit masks so that we can read the specific bit to see what button is pressed. Emulation is a really important part. It's going to speed up your development cycle dramatically. And a good emulator can be a great tool to help you debug and move quickly. So I use MGBA. You can put, there are views where you can see what palette colors are loaded, what tiles are loaded into memory, what the backgrounds currently look like. You can look into the actual memory of the console. There's a memory search feature. You can even look at the hardware registers to make sure everything's configured correctly. An invaluable tool. Would highly recommend you have at least some editor. MGBA has been great for me. And publishing. So this is something I think a lot of people kind of forget about when they are deciding to make a game. But really, one of the important things about making a game is like sharing that with other people. So you want to make sure that you have at least some idea of how you're going to get this game out to people when you start making it, because that's a tremendously motivating thing to see other people enjoy your game. So first off, we have GitHub, right? This is the default decision for publishing things as a developer. Just throw it up on GitHub, throw an open source license on it, maybe if you want to share it around. And yeah, this works. If you want to point people to your GitHub repo, they can go download your game, look at the source code, and run it for themselves. The problem is sometimes you want to share a game with somebody who doesn't want to install the Go compiler chain. You want to share the game with your dad or your brother who doesn't understand computers very well. So how do you do that? Well, I use a platform called Itch. You can make a free account. It's very easy to use. And basically it lets you construct a little storefront where you can stick up a download file, stick a couple of GIFs so that people can get an idea of what your game is all about. Would highly recommend. If you want to go play Flappy Boot, you can either get it from my GitHub or from Itch. And if you get all of that done, if you make all of that work together, what you end up with is this. A little game that you can play on an emulator. But here's the problem is like the title of this talk is like, let's make a game for the Game Boy Advance. And like MGBA is not a Game Boy Advance. Like this is a Game Boy Advance, right? Game Boy Advance is an actual physical piece of hardware. Woo! So how do we make that next step to actually get it to play on a real GBA? And the answer is there's a couple of different ones, but the one that I chose was the GBX card read write. It's a flasher. So you can buy from Inside Gadget this little flasher as well as, where I showed it earlier, but like physical flash cartridges that can hold your game. And if you also, the tool that comes with it is Flash GBX. And like, if you go through the process of building the game, you can flash it to a cartridge, plug it into an actual piece of hardware, and like turn it on. And there it is. You can actually. Any questions? Why? Best question, and the answer is why not? Yeah, I mean it's a totally ridiculous thing, but I like the GBA as a target for game development, in part because I think low level development is really fascinating and interesting. Go is a language that can support that, and also like the constraints of the GBA do a lot of favors to you in the fact that like you just can't go crazy. You can't make an MMO multiplayer shooter on the GBA. Like you get tiles and backgrounds, and those constraints can actually help it be easier to finish a game, right? So I think it's a good platform actually.
Where'd you get your art?
So I made all the art. I am a pixel artist in the evening sometimes. So yeah, I enjoy that in addition to my day job as a developer.
So you've thrown away the garbage collector. You've thrown away some of the memory mapping, or sorry, the memory model. What? But you mentioned that you still get some of the type safety with. How do you describe that? What other benefits do you see in using Go for something like this? So just C. So that's sort of the underlying thing, anyway.
Yeah, so that's a really good question. Actually, there's a couple of reasons. One is you don't actually have to totally throw out the garbage collector. If you decided to run the garbage collector more frequently, you could probably get away with a small game that still produced a bunch of garbage, and you're just doing a mark and sweep, not on the full heap. I haven't tested that, but I imagine that would totally be doable. You get the type safety. The big thing for me is the tool chain. I don't know if you've ever tried to build a project in C before, but it's kind of a headache. And TinyGo very much follows the Go ethos of just like you have a compiler and that's basically it. Like that's all you need. Install TinyGo and just build your source code. So like a lot of that complexity being taken out of this process is hugely beneficial.
How long do you think it took you? All the learning and everything.
Yeah, we're coming up on. So I finished this game several months ago. From start to finish, probably took me like 6 months to legitimately go all the way through the process. I would imagine if you wanted to do it from scratch, it would be easier because there are some references now that I've created where you can actually look at how to do something like this in Go. But yeah, it's not a short process. It's not going to be like a Unity tutorial where you could just jump in and make a game. That being said, I've started making another game, and that process is going substantially faster, right? So it's kind of that wall where it's like a lot of onboarding, and then like once you're on, then it actually smooths out. It's the learning curve is high, but then once you're into it, you're. All right, well, I'm going to be around for the rest of the conference. If you have questions, come chat with me. I've had some people ask for physical cartridges. If you're interested in that, hit me up on Forge Slack or like email me. We are giving a cartridge away, so maybe wait until you see if you win today. But thanks for everyone for coming, and let's go have lunch.